Guys, this is the continuation of our final section, integrals. So I think you remember we have discussed antiderivatives and the fundamental theorem of calculus here, right? So this is the definition of antiderivative, and we talked about the fundamental theorem of calculus. And today in this video we are going to discuss about this theorem here. So this one, suppose f is a continuous function on closed interval ab if uppercase f is an antiderivative of lowercase f on ab, then integral from a to b f of x dx is equal to uppercase f of b minus uppercase f of a. So we are going to prove this one, right? Let's see how we prove this theorem, right? So here we know that lowercase f is a continuous function on this interval, closed interval, right? Then and f is an antiderivative of f on ab. So let's define another function called g as follows. So let me take my blackboard. G is a function from G. Wait a second. So G is a function. Uppercase G is a function from AB closed interval to real number set, right? Let's define g of x. G of x as follows: trigger from a to x, f of x, f of t. Sorry, where's it? F of t dt. T is the dummy variable, right? So we know that in the theorem of fundamental theorem of the fundamental theorem of calculus, this theorem, we know that f is an antiderivative. Uppercase f is an antiderivative of f here. Look at this. So this one here. F uppercase f is an antiderivative of f ab closed interval. So that means g here, in this case g is also an antiderivative of lowercase f on AB interval, right? And we know that uppercase f is also an antiderivative. Now we consider we define another function called h. Is the difference between f uppercase f and g, right? And from the theorem of fundamental theorem of calculus, So when you differentiate G, uppercase G, what do you get? You get lowercase f, right? Right. So this is the first fundamental theorem, and so since f is also here, f is also an, here look at this, f is also an antiderivative of f. So that means when you differentiate uppercase f, you get lowercase f. Let's differentiate. So this is continuous. So this one is differentiable because f and g are differentiable, right? Then h also differentiable and continuous on closed interval a, b, right? Then we can differentiate h with respect to x, get f prime minus g prime. This one is lowercase f minus lowercase f. You get 0. So when you differentiate h, so you get 0 on this interval, on AB interval. So from mean value theorem, we can say that the function uppercase h should be a constant c, right? That means, so our capital H is defined as this simple c, lowercase c should be equal to f minus g, right? Then g, let's substitute g, let's isolate g. Uppercase g is equal to f, uppercase f minus constant c, right? So let's compute g of a. G of a is with uppercase f of a minus c. Uppercase g of b is equal to uppercase f of b minus c, right? Here just look at the definition of g here. So as the definition, here g of x is defined as this integral from a to x f of t dt. So what is the value of uppercase g of a? So this integral goes from a to the same point a. So we have learned that, so integral from a point to the same point is equal to 0. So g of a, simple a, is 0. So let's go to our writing here. So this is so g of a is equal to 0. This one is equal to 0. From here we get uppercase f of a is equal to c. Uppercase f of a is equal to c. So just sub. So we are subbing this one into here. And g of b is equal to f of b minus c. Here c is with uppercase f of a, uppercase f of a. Alright, so g of p, look at the definition again. G of x is this, then g of p is from integral from a to b. Okay, let's write that. Integral from a to b f of t, dummy variable t dt. Alright, we showed that integral from a to b f of t dt is equal to fb minus fa. F is an antiderivative. So f uppercase f is an antiderivative of f. So we are done. We showed this property. We proved this one. Right. So now let's look at the properties of integral. So integral is a linear operator here. Linearity. Let's discuss the properties of integral. So if you have a constant here this is a constant, a real number, any real number times the function f. So you can pull this out from the integral side, right? You can pull this out. This one is same with k times integral a to b f of t should be I don't know, that's alright. F of x dx. So if you have a sum of two functions, then this integral is same with the sum of integrals. That is another property. So this integral operator satisfies the linearity properties, right? Alright, so integral of sum of two functions is same with sum of integrals of each function, right? So this is called, this integral satisfies linearity, right? I hope you understood the proof of this theorem and this linear properties of integral, right? In my next video I'm going to talk about this one here. So more properties of this integral. If you have a non-negative function on this interval, then the integral also non-negative. Let's talk about that in another video, right? Alright, see you both.